Now let's solve some example. This one, for example, we have a Cobb-Douglas, which is this Cobb-Douglas U x1 x2. Suppose xy is x1 and xj is x2, and we have x1 to the power of alpha, x2 to the power of beta. So again, it's such that p1x1 plus p2x2 is equal to our income. In order to like economize our time, when we are giving like this kind of utility function, x1, for example, x2, x to the power of alpha, x1 to the power of alpha, x2 to the power of, for example, beta, or either assume that x1 to the power of alpha, x2 to the power of 1 minus alpha, which is beta is equal to 1 minus alpha. As I said, the first step, because, for example, when it comes to qualified exam, in qualified exam, we have limited amount of time, but maybe there are too long questions. If we do all the steps, so maybe we would not have enough time to solve all the questions, or even we would not to solve all the questions that help us to like pass the exam, because most of the students do not have the problem on solving the questions. They have problem on managing their time. So when we have like this kind of utility function, which is differentiable, or either 2 as differentiable, we need to do just optimization step. For example, the first step, set up optimization condition. Optimization condition. Because when professor can bring this question, will ask you to find out for example, Marshall demand, indirect utility function, or for example, expenditure function that we had in our midterm exam. She didn't mention that what kind of method or procedure or process you have to use. You have to use from the beginning. I mean, 7 score is much more better than 2 score, much more better than 0. If you cannot get 10, at least get 7. It's a good strategy. If you can be perfect, at least we need to be good. Yeah? Because at least we have to be in a way. So now set up the optimization condition. What is optimization condition? Marginal rate of substitution is equal to economic rate of substitution. We don't need to move to take the Lagrangian to do a lot of big process. Just here. So marginal rate of substitution is equal to mu x1 divided by mu x2 is equal to p1 over p2. And we know that mu x1 is equal to the partial derivative of this function, x1, x2 with respect to x1, which is equal to alpha multiplied by x1 to the power of alpha minus 1, x2 to the power of beta. Then mu x2 is equal to the partial derivative of u x1 x2 with respect to x2 is equal to beta multiplied to x to the power of alpha, x2 to the power of beta minus 1. Yeah? So now you find out this part. This part is already clear. Just in the next step, do this one. The alpha x1 to the power of alpha minus 1, x2 to the power of beta, beta, x1 to the power of alpha, x2 to the power of beta minus 1, cancel out. It will become to alpha divided by beta. Move x2 there and x1 here, x2 over x1. And this one is equal to your price level, p1 over p2. So now you have this one. Just then your x2 will become P1 P1 divided by P2 multiplied by beta x1 divided by this alpha. This is your x2. Yeah? And just in the next step, so this is the first step. The first step, set up optimization condition and find out one of the consumption good as a function of another one, which is this one. So now, the second step, substitute. Substitute to budget constraint. In budget constraint, we have P1 x1 plus P2 x2 is equal to m. So now P1 x1 plus P2 multiplied by this one, P1 over P2 Px1 over alpha equal to P1 P2 beta x1 alpha is equal to m. Cancel out. P1 x1 plus, then it will become to P1 beta x1 alpha equal to m. Then you have P1 x1, or either we can just this x1 is equal to, so now x1 we have P1, we have here, okay, even we can move further. P1, we can write down P1 x1 here, and this one we have we can have we can have 1 plus P1 is already here, then beta x1 alpha is equal to m. So now, as you know, this one, yeah, this one. So now we have our P1 x1. Here we have alpha plus beta is equal to m. So then we only need the x1. Divide everything to this one, m P1 alpha plus beta divided by alpha. When you simplify it, this one will change to alpha will move here. Then we will have alpha plus beta multiplied by P1. So now we have x1. Then we already find out our x2 in terms of x1. Just plug the value of x1 here. Plug the value of x1 star here, then you will find out x2. So just here we need two steps, 1 and 2. But if we want to do too much in detail, step by step, if we want to use Lagrangian multiplier, Lagrangian function, it will take a lot of time. So just set up the optimization condition and find one good in terms of another, or a function of another. Then substitute to budget constraint. You will find one of them. Then again, substitute this value to this function that you already found out as a function of another good. So now you will have x1 star and x2 star, both of them. So if you, for example, we have our x2 P1 over P2, P1 over P2, Bx1 over alpha, by B over alpha. Instead of x1, we can write down the value, which is alpha multiplied by m alpha plus beta. Then this alpha will cancel out with this alpha. So x2, I think, okay, we have one P1 here. Yeah. Then this P1 will cancel out with this P1. So in the numerator, we have beta multiplied by m. In the denominator, we have again alpha plus beta multiplied by P2. Just we need to follow this tree step and find out the x1 and x2. And this one, x1 and x2 are called the Marshallian-Demon function. And we use this Marshallian-Demon function in order to find our indirect utility function. Indirect utility function is a result of utility maximization process in terms of price and income. Because the indirect utility is a function of P and M. It comes from our utility when, for example, xi is a function of P and M, this xi star. Xi star is a function of P and M, and also xj star as a function of P and M. So when we plug the value, our xi and xj star as a P and M, so there will be no more xj and xi. Although in our utility function, in u xi, xj, we had, for example, xi to the power of alpha, xj to the power of, for example, beta. But we find out already the value that xi is equal to alpha multiplied by m plus alpha plus beta over the pi. And xj is equal to beta divided by alpha plus beta multiplied by m divided by pj. Then we already know that this xi, this xj are a function of m and p, because alpha and beta are constant. When we have the function, they know which is this is the share of x1 and this is the share of x2. So only we have xi. So let me clean this part. We have this xi star as a function of p and m. Also, we have this xj star as a function of p and m. Then, if we plug the value of xj star and xi star in terms of m and p in this function, what we will receive? We will receive the indirect utility function. Why this is indirect and why that is direct? Because here, your utility is directly related to the consumption. Where we like take our utility, we get our utility from consuming goods. So this is a direct utility function because it's directly related to consumption. But this is indirect because this is not directly related to consumption, but it's related to P and M. But P and M is related to xi and xj. So it's a kind of directly give you the utility out of paying this price using this income to have this utility function. So then, for this Cobb-Douglas, our VPM is just simply, we need to add this xi and xj instead of xi and xj here. So it will change to, we have xj, this one. Just write down alpha multiplied by m, alpha plus beta multiplied by p. For example, now as we worked on x1 and x2, for example, this one say xp1 to the power of alpha multiplied by, again, sorry, beta. This one is beta multiplied by m divided by alpha plus beta multiplied by P2 to the power of beta. So we can, as you know now here, this function is a function of M and P. Although still we have this alpha and beta in this function. But no more we have x1 and x2. For example, let's suppose this one is u, x1 and x2 is equal to x1 to the power of alpha and x2 to the power of beta. So in this utility function, we have x1 and x2, and also alpha beta and as a share of x1 and x2. But here we have no more x1 and x2, but rather we have m, p1 and p2. So as this is as a function of p1, p2 and m, this one is called indirect utility function. We can simplify more also to raise to the power. How we can simplify this one? Is there any way? As you see this m, we can change this m as this one, m to the power of alpha plus beta, because we have m to the power of alpha, m to the power of beta. Yeah? So let me here we have VPM is equal to alpha plus beta P1 to the power of alpha, then beta divided by alpha plus beta multiplied by P2 overall to the power of beta multiplied by m to the power of alpha plus beta, m to the power of alpha plus beta. And one of the reasons that mostly why we assume that this alpha plus beta is equal to 1 in order to find our expenditure function easily. Our expenditure function easily. Why? Because this alpha plus beta is equal to 1, then this function will change to V PM, then will be equal to, for example, alpha to the power of alpha, P1. This one will be equal to 1. Then we will have this function, alpha, P1 to the power of alpha. Then this one will change to 1 minus alpha divided by P2 to the power of 1 minus alpha multiplied by M. Multiplied by M. So when this is the first step, the last step of indirect utility function, if alpha plus beta is equal to 1. This is the indirect utility function if alpha plus beta is equal to 1, because when this is equal to 1, so it will change like this, alpha plus 1 minus alpha. Alpha cancel, just 1 will remain here. So now, one of the things, when we are finding our expenditure minimization, we think that the utility that we receive from P and M, we receive it from the maximization of UX as we get something U star or U bar, anything you like. And also the EPU, which is our cost expenditure minimization, is equal to the mean of PX, which is equal to M. The mean of PX, which is equal to M. So now, we find out our indirect utility function, VPM. So let me more precisely write down this one. V, P1, P2, and M, which was equal to alpha over P1 to the power of alpha, then beta, alpha minus 1 alpha minus 1 over P2 to the power of, what was here? To the power of 1 minus alpha. To the power of 1 minus alpha multiplied by m. So now, your m is equal to EPU. And your indirect utility function, VPM, is equal to your U. So then, substitute those two values here. Then we will have this one. Instead of V, P1, P2M, just simply write down this U. Just U. Then alpha over P1 to the power of alpha multiplied by 1 over alpha over P2 to the power of 1 minus alpha. And instead of M, write down E, P, U. This EPU is your expenditure function. So now, if you want to find out this expenditure function, so divide both sides to this term. Both sides to this term. Then what will remain? You will remain with this one. EPU is equal to U divided by alpha over P1 to the power of alpha multiplied by 1 to the power of 1 minus alpha over P2 to the power of 1 minus alpha. So then we can more simplify this one. So then EPU will be equal to P over alpha to the power of alpha, P2 over 1 minus alpha to the power of 1 minus alpha multiplied by U. So this is your expenditure function. Your expenditure function. So the thing is, once we find out our Marshallian Demon function, then we can find out indirect utility function. Once we have indirect utility function, we can find out expenditure function. This is the process. Find out we have our direct utility. By maximizing direct utility, we will move to find out Marshallian Demon function. Marshallian Demon function. Then, by finding Marshallian Demon function, we can find out indirect utility function. By finding indirect utility function, we can find out our expenditure function. And by finding expenditure function, we can find out the Hicksian demand function by using Shepard's lemma. So that's why we call it there is duality. It comes from Marshallian Demon function moved to Hicksian Demon function. You can work other way around. For example, if you have your Hicksian Demon function, you can find out your expenditure function. When you have your expenditure function, you can find out indirect utility function. When you have your indirect utility function, you can move out to find out your Marshallian Demon function. Why? Because if you have Hicksian Demon function, in Hicksian Demon function, you have this function x to the power of h, as a P and U. And also in expenditure function, you had E as a function of P and U. E as a function of P and U. So if you have this one, you can find out this one as well, because both of them as a function of same thing, P and U. If you have expenditure function based on this duality that we already worked here, based on this one, so as we have here, for example, in our function, we have M. So instead of M, so this time, instead of M, this time write down EPU. When you have EPU, then instead of EPU, write down M. So let me tell you again. If you have M, and someone asks you to find out expenditure function, then add EPU instead of M. But if you have EPU, and someone asks you to find out indirect utility function, just add instead of EPU M. Just add instead of EPU M. Let's do it. For example, where was our expenditure function? That one. That we have E P U is equal to this one. Where was the last? The last one is here, yeah. Which is equal to P1 over alpha to the power of alpha, P2 over 1 minus alpha to the power of 1 minus alpha. And we have U there. If you have expenditure function, and if someone asks you to find out indirect utility function, what you will do? Can you tell me what you will do? If you have this expenditure function, someone asks you to find out the indirect utility, then what we will do?
Move by U.
So we will move to this duality condition. Our VPM was equal to U. Just write down instead of U, V, P1, P2M. Our EPU based on this duality condition is equal to M. Then write down instead of EPUM. Then you have this function, which this function is a function of M, P1, and P2. So now you have expenditure function, you found out the indirect utility function. So then if you have indirect utility function, you can find out the Marshallian demon function by using Roy's identity. By using Roy's identity. So now, let's see what is Roy's identity. And also what is Shefford lemma. Roy's identity is this one, that x I, for example, as a function of P and N, is equal to a partial derivative of utility function with respect to the price of this good, which is Pi, divided by the partial derivative of utility function with respect to income.
Not V, right?
Which one? This is V. This is M. Let me say again. Roy's identity is a formula to find out the Marshallian demon function. For example, let's suppose this Marshallian demon function is xi and x2, anything you can find, is equal to negative minus the partial derivative of utility with respect to price divided by the partial derivative of indirect utility with respect to income. With respect to income. This is called price marginal utility, this is called income marginal utility. Because as you know, for direct utility function, when we take the partial derivative of direct utility function with respect to SI, we call that marginal utility. But here, this is price marginal utility. This is income marginal utility. Or you can say marginal utility per dollar of income, or marginal utility per unit of price. Income marginal utility and price marginal utility. So if you find out the price marginal utility, divide that one to income marginal utility, but having negative sign. Why having negative sign? Can you tell me why we have a negative sign here? Think about this. We have price, we have income. Relate this one to utility. If the income increase, if the price increase, what will happen to utility?
We don't know.
We know.
Maybe the utility will decrease. Maybe
For example, if there is no change in your income is fixed. As we said before about the income effect and substitution effect. If the change in price is something positive, for example, let's say it's K, any number, but the change in income is 0, then what will happen to your utility? Utility will be decreased. And if the change in income is something positive number, for example, let's suppose it's as a, again K, but the change in price is equal to 0, what will happen to utility? It will be increased. That's why as when we take the partial derivative of our utility with respect to price, so it will have a negative sign. Then we should multiply the another negative sign with that negative to make it positive. Because the demand function should be positive. As we said, you cannot consume negative amount of something. You should consume either 0 or positive. Then, as price increase, utility decrease, so the partial derivative of income with respect to price is negative, while the partial derivative of utility with respect to income is positive. Then negative divided by positive, what will be the result? Negative. Then you need another negative to make it positive, to have a positive or at least 0 amount of consumption. So this is called the Roy's identity. By using this Roy's identity, we can find out the Marshallian demand function. So we have our VPM, VP1, P2, M. Where was that? VPM here. Alpha, okay. Which is equal to alpha over P1 to the power of alpha, then 1 minus alpha over P2 to the power of 1 minus alpha M. So now, if we find out x1, then x1 is equal to minus the partial derivative of V, P1, P2, M with respect to P1, then the partial derivative of V, P1, P2 with respect to M. Can you find? You have to find out this result, which is x1 is equal to alpha MP. When you use that Roy's identity, the result of x1 star should be equal to alpha divided by P1 M, x2 star should be equal to 1 minus alpha M divided by P2. You should exactly find out this one. Shefford lemma. It's easy. When we want to find the action demand function, which is a function of P and U, just simply take the derivative of expenditure function H with respect to Pi. Xjh is equal to all partial derivative of expenditure function with respect to Pj. So now, if I is equal to 1 and j is equal to 2, then it will change to x1h as a function of P and U is equal to the partial derivative of expenditure function with respect to P1, and this one x2h will become to the partial derivative of expenditure function with respect to P2. Just easy. This one is easy, doesn't need too much work. But the thing is, so for example, where was this one? EPU P2 plus alpha, okay. We have EPU, it was like this, P1 to the power of alpha, P2 over of alpha, 1 minus alpha to the power of 1 minus alpha, multiplied by U. So now, take the derivative of this function with respect to P1. You will find out the x1h as a function of P and U. And again, the EPU is equal to P1 over alpha to the power of alpha, P2 over 1 minus alpha to the power of 1 minus alpha multiplied by U. So then, x1h is equal to the partial derivative of EPU with respect to P1, which is equal to now alpha multiplied by this alpha to the power of alpha multiplied by P1 to the power of alpha minus 1. Then you have P2 1 minus alpha to the power of 1 minus alpha U. Then we'll have x h star is equal to this alpha. Here we have 1 plus alpha multiplied by P1 to the power of alpha minus 1 multiplied to the P2 to the power of 1 minus alpha multiplied by 1 minus alpha to the power of alpha minus 1 multiplied by utility. So we can write down this one as x1 h star is equal to alpha divided by 1 minus alpha to the power of 1 plus alpha, because when we move this one to the denominator, so that the sign will shift. So multiplied by P1, so move the P2 here, P2, again the sign of P2 will shift, alpha minus 1, multiplied by U. So now, as you see, this x1 h star is equal to alpha over 1 minus alpha to the power of 1 plus alpha multiplied to P1 over P2 to the power of alpha plus 1 multiplied by U. Minus 1, yeah. Alpha minus 1. And now, this x1 star h is a function of P and U. Is a function of P and U. As we already have the expenditure is a function of P and U. This one is also as a function of P and U. So this one is Hicksian demand function. Hicksian demand function is directly related to expenditure function. Why? You can see here, Hicksian demand function is a function of P and U, and expenditure function is also as a function of P and U. Both of them, they are directly connected. But the Marshallian demand function, is directly connected with indirect utility function. Because the Marshallian demand function x star is also as a function of P and M, and indirect utility function is also as a function of P and M. So that's why when you use Roy's identity, when you have indirect utility function, it will gives you the Marshallian demand function. But when you have expenditure function, you can use Shepard lemma to give you the Hicksian demand function. And that's why we say that there is a duality exists. And also that x star PM is equal to x h star as a function of P and U. As a function of P and U. So why is this? Because this M is a function of P and U. We know that we, instead of M, we can write down E as a function of P and U. So now this will change it to x star P, and instead of M, you can write down EPU. Then here, XH star is a function of P and U. As you see now, this is also as a function of P and U. This is also as a function of P and U. That's why when we talk about duality, in terms of duality, as I showed before in the graph, that the optimal point is the same. Although the graph, the slope of the graph or the steepness of the graph is different, but the optimal point is the same. So in terms of duality, the x PM is equal to the xh pu, because this m is a function of pu. So it's simply x p e pu and x h as a function of pu. So now you have two demand functions and the two sides of equality, which both of them are a function of P and U. So now we have no more M here. For this one we have P and U, for this one we have P and U. That's why we call it that there is a duality exists between Marshallian demand function and Hicksian demand function. This is the duality. Okay, this is what we had today from the beginning up to the end. So the final things, either we work on utility maximization or expenditure minimization, we will move exactly to the same result. And also we can move backward. Either you move forward or you move backward, you will have the same result.